Welcome everyone, I am Federico Trinca and I will be talking about Cayley vibrations in the Bryan-Salomon manifolds. Let me first thank Ojo Lee and Jesse Madnick for organizing this event and for inviting me. So the first thing that I'm doing is to give you an overview of what I will be talking about. So my talk is going to be divided into 3 videos. In the first one, I will be talking about spin 7 geometry. So I will give you some basics on spin 7 geometry, calibrated geometry, and what I mean by Cayley vibrations, which are going to be the main objects of the talk. The second video will be about the Bryan-Salomon manifold. So I will recall the structure induced by the spin 7 structure constructed by Bryan and Salomon on the negative spinor bundle of S4. I will explain all this terminology in that lecture, in that video, and I will also describe the automorphism group, because essentially the idea behind my construction is to use symmetry reduction, dimension reduction, however you want to call it, and so we are interested in subgroups of the automorphism group of the Bryan-Salomon manifolds. Finally, in the last video lecture, I will say something about, I will describe the Cayley vibrations that one can construct in the Bryan-Salomon manifolds. This is based on my work, which is a preprint and that you can find in archive. Okay, so here we are to the first part, so spin 7 geometry. So the local model that I would like to keep in mind, that I would like you to keep in mind, is R8, seen as 2 copies of R4, and I put the standard coordinates x0, x3 on the first R4 and A0, A3 on the second R4. Now we can endow this space with a 4 form, which we call, well, this is the standard Cayley 4 form, which is usually written as phi, big phi. So phi over 8 is defined as dx0, dx1, dx3, da0, da1, blah, 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 da3, plus the sum for I equal to 1 to 3 of omega I wedge eta I. So omega I, omega i's are the standard basis of anti-self-dual true forms on the first copy of R4. So this is just to indicate that we're working on the copy parameterized by x0, x3. And analogously, the eta i's are the one that we have on R4 So explicitly, this is something like dx0 wedge dx1 minus dx2 wedge dx3 is the omega 1. Omega 2 is dx0 wedge dx2 minus dx3 wedge dx1. And finally, omega 3 is dx0 wedge dx3 minus dx1 wedge dx2. So the Cayley form can be seen as the volume of the first copy of R4 plus the volume of the second copy of R4 plus the anti-self-dual part. So why this 4 form, which might look random, is related to spin 7, and the reason is due to this proposition. So the subgroup of GLR8, which reserves phi over 8, so the subgroup, the stabilizer of this 4 form is isomorphic to spin 7. Now we have a local model, but we want to pass from the local model to a global model. So the setup is now an 8-dimensional manifold M, and we put a 4 form phi on it. So this phi is said to be a spin 7 structure or an admissible 4 form if it admits a linear isomorphism I of x from R8 to Txm such that Ix star of phi is equal to phi of R8 at each point of M. So what does it mean? It means that we are identifying R8 with the additional Cayley 4 form, so the local model with the tangent space and our global 4 form. So the spin 7 structure, it is well known that it induces a Riemannian metric G phi and an orientation vol phi on M. So these are the metric and the volume form that make the identification I of x in orientation preserving isometry. Now, why these spin 7 geometry, spin 7 manifolds are interesting? Well, spin 7 structures are not actually that interesting because these are completely characterized by topology. So there is a proposition due to Lawson-Michelson. And they proved that an 8 manifold admits a spin 7 structure if and only if some topological conditions are satisfied. So we need to put some additional structure, some additional condition on our 8-dimensional manifold, and the right condition is to require this 4 form to be closed. So a spin 7 manifold is a 8-dimensional manifold M together with a spin 7 structure phi such that phi is closed. What I would like to point out as well is that in this situation, the holonomy group of G phi is contained in spin 7. So in a way, we are reducing the holonomy of our manifold from being just some SO8 to having holonomy spin 7. So now let me briefly say a couple of things about calibrated submanifolds. This might look quite not related to the previous 2 slides, but I then will explain why calibrated geometry plays a role here. So given a Riemannian manifold, so no 8-dimensional object here, we say that a K-form omega is a calibration if it is closed and has comass less or equal than 1, which means that omega of E1 EK is less or equal than 1 for all unit E1 EK. So given tangent vectors, unit tangent vectors, if we plug them into omega, we get something which is less or equal than 1. A submanifold sigma of dimension k, so we have matching dimension, is said to be omega calibrated if the volume form of sigma is equal to omega restricted to sigma. So let me just tell you something about this condition. So observe that omega is just some differential geometric object, a K form, while the volume of sigma is a K form on sigma induced by the Riemannian structure. So we are just trying to match the volume form induced by the immersion or embedding, depending on your favorite kind of submanifold, into we're trying to match the two objects. Now, why should we care about calibrated submanifolds and calibrated geometry? Well, the main reason is because of this proposition here. So the proposition is as follows. So given a calibration on some Riemannian manifold Mg, and given some sigma k dimensional omega calibrated submanifold of M, what it is true is that sigma is homologically volume minimizing. So in particular, it is a stable minimal submanifold, and hence a very interesting object from a Riemannian point of view. So the proof goes as follows. So we start from the volume of sigma. So the volume of sigma is just sigma times omega. So is the integration of omega over sigma. Now, the reason for this is by the calibrated condition. So instead of omega, we should put the volume of sigma, but they are equal. So they agree. Now, by the property that omega is closed and that sigma and sigma prime are chosen to be homologous to each other, we get this equality here. And now by the Comas condition, the inequality here holds, and this is just the volume of sigma prime. So in particular, we've proved that given sigma prime homologous to sigma, the volume of sigma cannot decrease. Sorry. Okay, so it's not surprising by the definition that phi, our Cayley form, looks very much like a calibration. And indeed it is true. So given M phi a spin 7 manifold, phi is a calibration. Indeed, well, the closedness condition is guaranteed by the torsion-free condition, and the Comas condition is granted by the spin 7 structure itself. So the metric induced by the spin 7 structure is such that the co-mass of phi is less or equal than 1. Now, a four-dimensional submanifold then is said to be Cayley if it is calibrated by phi, which means that when we restrict phi to n, we get the volume of n. So this is just a rephrasing of the calibrated geometry condition that we stated just one slide ago. Working with calibrated geometry and with a calibrated condition is not as convenient as one can think of. So there is this proposition characterizing Cayley submanifolds. So we have a omega true-valued four-form tau such that up to orientation n is Cayley if and only if this form vanishes on n. So what does it mean? So it means that we have a global tau which takes four vectors and spits back a true form, and when we restrict this to a Cayley submanifold, it is 0. So given four tangent vectors of our ambient manifold, I'm not writing down the explicit formula, but one can check on many papers about spin 7 geometry and Cayley submanifolds that tau depends on the interior product of this vector with phi. So we want phi to be in a nice form and on the metric, because we will use musical isomorphism. Okay, so now let me say something about Cayley fibrations, and let me start with a motivation. So why someone would care about this object called Cayley fibrations, that we could have a naive definition. So the naive definition could be something like a Cayley fibration of a spin 7 manifold M is a fiber bundle whose fibers are Cayley submanifolds. This is a completely fine definition, but it is sensible to look at definition that allows the fibers to be singular and to intersect. The reason comes from the motivation. So the motivations can be seen into two parts, if you wish. So one comes from physics. One motivation is physical, essentially. So as some of you might know, or probably know better than me, special Lagrangian fibrations on Calabi-Yau manifolds are expected to exist and to come in pairs, and this is called the SYZ conjecture. And so this SYZ conjecture relates dual Calabi-Yau manifolds to dual special Lagrangian fibrations, and we expect something similar to be true in the Cayley setting. So the second reason is mathematical and could be, and it essentially goes as follows. So knowing Cayley fibrations could help us construct new spin 7 manifolds, and compact spin 7 manifolds in particular. So we've given a naive definition, and I said, well, maybe we are more interested in Cayley fibrations with singularities and with intersections because of the motivations. Indeed, I didn't say that, but in the SYZ conjecture, so let me go back one slide. In the SYZ conjecture, fibers need to be singular and are allowed to be singular, and in the same way, if we want to construct interesting spin 7 manifolds, we will have to have singularities as well. So the definition is as follows. So it is very similar to the definition given by Karijanis and, well, Lotte. So they've done a similar work for cross-associative submanifolds in G2 manifolds. So my definition is very similar here. So a Cayley fibration on a spin 7 manifold, M phi, is a family of possibly singular Cayley submanifolds, and B, where B is an element of a parameterizing space curly B. And we also want to have the following properties satisfied. The first one is that we want M to be covered by these Cayleys. Sorry. This is not surprising, as we want something that looks like a fiber bundle, essentially. The second property is that there exists an open-dense subset curly B naught contained in curly B, such that NB is moved for real B in curly B naught. So this means that apart from an open dense set, it's only on the complementary of an open dense set that we can have singular fibers. And the last property is that we have a open dense set M prime of our big space M, and the smooth fibration pi, so a non-nest fibration fiber bundle with fiber NB intersected M prime for every B. So the explanation is as follows. So we have M minus M prime is the set where the fibers are singular or intersect, and the complement of B curly B naught corresponds to the Cayleys that develop singularities or can develop singularities. Okay, so the goal of the next 2 videos is going to prove the following theorem, which goes as follows. So on every Bryan-Salomon spin 7 manifold, which we will describe next video, we consider a natural family of SP1 actions on it, and for every element of this action there exists a, well, possibly singular and with intersections. So we have a Cayley fibration, which is SP1 invariant in the sense of the definition of the previous slide. Let me just give you this idea. So that the main idea is essentially to use these SP1 symmetries to reduce the problem to a system of ODEs. And that's it for this first video, and hope you enjoyed it, and I'll see you at the next one.